Hello, everyone. Welcome to this fifth webinar of our spring webinar series. Today, I have the great pleasure of hosting this webinar with Professor Jochen Autschbach from Buffalo University in New York. Jochen has been a long-time developer and collaborator of ADF and SCM. He did a postdoc with Thomas Ziegler, one of the founders of the company. And he's an expert in spectroscopic properties and has developed many methods in ADF. And today he will be talking mostly about NMR shielding, J-coupling and EFG analysis with NBOs. And yeah, the floor is yours, Jochen.
Yeah, thank you. And thanks for hosting the webinar. So I wanted to talk today about some relatively old developments related to the analysis of NMR parameters from relativistic DFT calculations. I thought, though, this is still timely because these methods have been proven to be quite useful over the years, and we've seen some renewed interest in this recently. Okay, so I want to go over some slides first, and then later, if I don't run out of time, I thought I'll share a small demo with the graphical user interface that I personally don't use very much myself, so I hope this will go well. If you're viewing this on a phone, the slides should work okay. With the demo later, I'll have to share a larger part of my screen. I'm not sure if that's suitable to view on a phone, although maybe you'll be able to follow it by zooming in. Okay, so first, I want to talk about the analysis of spin-orbit relativistic calculations of shielding and J-coupling. To those of you who are not familiar with these types of calculations. So in the NMR experiment, the two main observables that present themselves for isotopic samples, so when you have a solution phase measurement, for example, the chemical shift, which is related to the nuclear magnetic shielding by this difference here that's similar to what they do in the experiment. They need a probe and a reference, and so do we in the calculation. But the fundamental variable underlying the chemical shift is the nuclear magnetic shielding, which is a rank 2 tensor written here with these two dots to indicate the tensor rank. Also, I guess this kind of notation is dear to me since I grew up in Germany. Anyway, so there we have a second derivative of the molecular energy with respect to the presence of a spin magnetic moment of a nucleus and the external field applied in the spectrometer. Then this is sort of the phenomenological Hamiltonian here, where I put the cursor, and then the calculation goes through this route here. The splitting of the signals, that's determined by the indirect nuclear spin-spin coupling, the so-called J-coupling, which is parameterized by this Hamiltonian shown here in the upper right of this slide. There's a coupling tensor K, that's also a second derivative of the energy here with respect to the components of the of a pair of nuclear spin magnetic moments, so one here, and then as you figure out how they interact with each other magnetically, you can extract the spin-spin coupling. Which means if the energy is relativistic, then so are the calculated parameters. And as some or most of you know, NMR parameters are famously sensitive to relativistic effects. So the second aspect I wanted to cover is that people like to analyze their calculated results, for example, in terms of molecular orbitals, chemists live and think and breathe molecular orbitals all day. And so that's an interesting thing to do. Now, NMR parameters are determined by electronic structure that is sort of local to the atoms for which the NMR parameters are determined. And it turns out that the analysis also best proceeds in terms of localized molecular orbitals. So I'm showing here, for example, the famous case of benzene, where we all know that the pi system cannot, in fact, be localized. So on the left, we're looking at some canonical molecular orbitals as they come out of the SCF calculation for sigma down here, pi up here. If you localize the orbitals on the right, you get well-localized sigma orbitals, which I represent here by contour line diagrams in the molecular plane. And the pi system is delocalized. That means if you try to localize it, that does not go well. So I plotted here in a plane above the molecular plane, the 3 occupied pi orbitals, and they are very strongly delocalized. But that is information you get out of the localization procedure. In the NBO program, on which I will focus here in this talk, so when you generate localized orbitals with the natural bond orbital program that's included in the ADF distribution, I guess, you get these orbitals that are localized as much as possible, which means for benzene, it's not very localized. And the NBO code sort of constructs an underlying so-called parent NBO that is ideally localized and supposed to correspond to something that you can associate with the Lewis structure. And then on top of that, we get a delocalization tail that basically quantifies how strong is the delocalization of this particular orbital. And in the context of analyzing NMR parameters, it turns out this is a very useful concept that helps us understand the results much better than you get, let's say, from an analysis in the regular canonical molecular orbitals. Okay, so the developments that I want to discuss today, they took place mainly around 2007-8. The status at the time was that Meinhold and co-workers had formulated NBO-based analysis for nuclear magnetic shielding, and also there was a finite field approach for a contribution to the J-coupling available. But for the field that I was interested in, which is heavy metal NMR, there was no suitable available method. So I decided to implement this in a general way, so we can do analysis for all types of NMR nuclei all across the periodic table. Somebody in the audience has their microphone turned on. There's quite a bit of background noise. If you could perhaps mute yourself, that would be great. Thank you. Okay, so NMR shielding, J-coupling, fully analytic. We want relativistic treatment that is as general as possible, but also simple. So we do this with spin-orbit coupling and the zeroth order regular approximation or Zora Hamiltonian. And later I'll also show you quickly how to apply this to analysis of electric field gradients. Some of the references are shown here. If you like, look them up later, please. So as I said, today's topic is the analysis in terms of the orbitals produced by the NMBO program. You can also perform analysis, of course, with canonical MOs. There are other localization methods one can use, such as Boyce, Pipek-Mesai, Edmiston-Rüdenberg, and so forth. That's available to some degree in the code. And one can also generate property density functions, right? So if you have a quantum mechanical observable, you can always calculate it in some way or another by integration. And through that define, however, not uniquely, property density functions, and some people have very heavily focused on that type of analysis. Okay, so let me then show you very quickly how this is done. I want to sketch out the underlying machinery very briefly and then show you some examples. So at the time when I considered implementing this, the then current NBO version was 5, with about, I don't know, 30,000 or so lines of code. And I then decided that it would not be desirable to redevelop NBO to work with two-component relativistic spino-orbitals. And so instead, what we do is we use ADF and calculate two-component MOs, which I write here as a vector that's meant to be a spinor, not a proper vector, but what matters is that you have an alpha and a beta spin component to every molecular orbital. Then we do a second calculation where we exclude the spin-orbit interaction to get scalar relativistic orbitals. And then we can map the matrix here, that's the matrix representing the two-component orbitals, onto the full set. So here we use the occupied two-component orbitals and map it on the full set of the so-called external, as I call them in the publication. So the scalar relativistic secondary set of orbitals to provide a match between the two calculations. And then the coefficient matrix of the scalar relativistic molecular orbitals can then further be decomposed. I write this here as a matrix product BWT. So B is the matrix that represents the NBOs and the AO bases. W represents the NLMOs, the natural localized molecular orbitals in the basis of NBOs. And T is the transformation between the scalar relativistic canonical MOs and the scalar relativistic NLMOs. And so that's how the connection between the two calculations is done. And that's how we get NBO into the two-component calculations. Here's the expression for a second derivative property, such as NMR shielding, J-coupling, but you can also use this more generically for other types of properties, such as polarizabilities. So typically what you have is a mixing matrix that represents the perturbed orbitals in the basis of unoccupied unperturbed orbitals. There is a corresponding Hamiltonian matrix in that molecular orbital basis as well for the perturbation. And for magnetic properties, we also have what's called a diamagnetic term that's calculated from the occupied orbitals only. And so this is how you can represent a bilinear double perturbation property, such as the NMR parameters that we're concerned with. And then plugging in all these expressions from the previous equation, you get that same property just as a sum over many more terms. And we plug in here this combination of these NBO-related transformation matrices. And then in the end, you can sum over all these other terms and just leave out either the sum of over the NLMOs, or you can leave out the sum over the NBOs, and then you get an analysis of the property either in terms of the NLMOs or the NBOs from the calculation. And that is, of course, all hidden in the code, and it's not calculated as a 1, 2, 3, 4, 5, 6, 7 fold, 8-fold sum. That's not how it's implemented. It's more efficient than that. But in principle, that's how it's done. For the shielding, just briefly, because we work in a basis set of gauge including atomic orbitals, and so therefore the previous expression gets a little bit modified. There are a few additional terms, but the principle is exactly the same. So you get this nested sum, and in the end, for the analysis, you either decide to do the analysis in terms of NLMOs or in terms of NBOs. The code prints out both for convenience, so you can choose which one you want to look at when the calculation is done. And furthermore, these quantities that we're analyzing are ranked to tensors. So what the calculation does is it determines the so-called principal components of these tensors first, and then performs the analysis in a coordinate system in which the corresponding property tensors are diagonal. So you can get the analysis of the individual principal components and then their sum, or rather their average for the isotropic shielding or for the isotropic J coupling. And you can also analyze the anisotropy of these quantities in the same way. So here, I hope this is not too small to see on your screen. It's just one of the earlier examples that I studied. We're dealing here with the diatomic thallium iodide. And this molecule is known to have extremely large spin orbit effects on the J coupling between the two nuclei. That's some research that came also out of the experimental community. Dave Bryce and Rod Vasilishin figured out how to extract these quantities from molecular beam spectroscopic data. And so we know gas phase tensor isotropic and anisotropic components to the J coupling tensor. So here the results are listed in terms of this reduced coupling K that I showed earlier. And the total calculated here, this is from an old calculation using just LDA functionals, but it illustrates the principle. When you do scalar relativistic, you get something on the order of minus 900, and with the spin orbit, you get something on the order of minus 4,000, and the experiment is in that range. I think it's about minus 4,400, if I remember correctly. And these tables, they appear like this in the publication, but you also, it's basically a copy paste from the output. So there's an output that lists the NLMOs, it lists what the NBO developers call the Lewis and the non-Lewis contribution. I will just switch back a few slides here just to remind you. That's basically the contribution associated with the parent NBO and the delocalization tail of a given NLMO. So you get the contributions here to the J coupling separately. And you can see, okay, there's a bond between the two atoms. No big surprise that that is the bulk of the coupling constant and one of the iodine lone pairs and one of the thallium lone pairs, and some contributions from the heavy elements outer cores, which you always see. And then in the presence of spin orbit coupling, this is analyzed in the publication. Basically, the spin orbit interaction induces a sigma pi mixing in the occupied MOs, and it also causes some mixing of occupied and unoccupied molecular orbitals. That is, if you use the scalar relativistic orbitals to represent the spin orbit results, you see that kind of mixing occurring, and that is responsible for these very dramatic effects here. But otherwise, the analysis also gives a very simple and clear picture of these results, and most of the coupling is transmitted by the bond, as you would expect. Here's another of these earlier examples. This is Plumbane, so PBH4, the heavy methane analog. And we're looking at the coupling constant between lead and the proton. So the HOMO level is triply degenerate. Here in these calculations, you cannot use symmetry, unfortunately. So you get these symmetry mixed components of the HOMO, but still identifiable. And then the HOMO -1 has this symmetry. If you take linear combinations of these orbitals, you get the individual lead-hydrogen bonds. The one that is associated with the pair of nuclei for which the coupling constant is calculated gives you the bulk of the coupling constant. And then the other bonds have negative contributions. And that is because the NLMOs, as well as other types of localized orbitals that you can use here, are mutually orthogonal. And that means there are contributions of these orbitals on the lead and the proton for which we calculate the coupling, which is H1 here. And that takes electron density out of that particular interaction and has therefore this sort of counterbalancing effect. And then the total here is a scalar and spin orbit. I remember also this agrees very well with experimental data and with higher level calculations. Here's an example I wanted to show you to illustrate the importance of these delocalization tails. So here we had a compound that we were interested in, which has a platinum and a thallium center. So we're dealing with two heavy nuclei. And the J coupling between those nuclei is enormous. It's experimentally 147 kilohertz. That is, I believe, still the world record holder for the largest heteronuclear J coupling constant known from experiment. If you convert this to the reduced coupling, you get this 9,600 times 10 to the power 20 Tesla squared per joules. And it is well reproduced by these DFT calculations. So then you find, if you analyze this coupling in terms of canonical regular molecular orbitals, you get a lot of contributions from different orbitals that mutually cancel each other. And those orbitals all have a more larger, smaller contribution from the two heavy atoms. When you localize, basically all of the coupling constant gets absorbed in the single contribution, which is from the bonding orbital between the two heavy atoms. But it comes with a very large non-Lewis contribution, which has to do with the fact that there's this three-center delocalization here in this system, which takes electron density out of the bond and delocalizes it over the other nuclei. And so quite intuitively, I believe this has a negative contribution to the coupling. So I feel like this type of analysis is quite useful. My other example, and I will show you in the demo later, one quick example of this is analysis of platinum chemical shifts. So here's just a plot showing our calculations. This is at the GGA level. DFT with GGAs correlates with experiments. So here, ideally, we would like to see a slope of 1, but the slope is about 0.85. The slope becomes 1 when you go to hybrid functional. So PBE0 with spin orbit coupling performs extremely well, but these are older calculations where we didn't use that. And so as an example here, square planar PTCl4 versus octahedral PTCl6, both are 2- charged complexes. And then the shift is basically PTCl4 versus PTCl6 as the reference. And you can see that the total difference mainly has to do with contributions from the platinum non-bonding 5D orbitals. That is what produces most of the chemical shift between these complexes. And the analysis is also very clear in why this happens. So basically, if you have some kind of magnetic coupling when the magnetic field acts on these d-orbitals in the valence shell, people have used these so-called orbital rotation methods to describe this influence of the magnetic field. So if you have a d orbital and you have a field in z direction, this the perturbed orbital will basically amount to a rotation of the original orbital, and that orbital then has to overlap with unoccupied orbitals that have a sigma star antibonding character in order to generate a large contribution to the shielding. So in the article, and also that's the article right here, and also on my webpage, I provide some information about how you apply these orbital rotation models. But the bottom line here is that in PTCL6 2-, you have the dxz, dyz, dxy occupied, and each one of them generates a very, very large paramagnetic d-shielding, whereas in the square planar complex, there is one orbital like this, that's the in-plane dxy that's occupied, that creates most of the d-shielding, and the other two orbitals are much weaker, and that has to do with the fact that the complex is square planar. So there are no antibonding orbitals perpendicular to the plane available for the magnetic coupling. So well, you will please memorize this number here. I'm going to show you this later in the output. Okay, and then briefly, in the interest of time, I want to talk about field gradients. So this is of interest to solid state NMR spectroscopists very much, because if you have a quadrupolar nucleus, there is the nuclear quadrupole coupling mechanism that sort of superimposes itself onto the shielding J-coupling type mechanisms in the solid state NMR spectrum. And then you basically have additional parameters that you can extract from the measurement that give you information about the electronic structure. So the quadrupole coupling is related to this V33 here, which is the largest component of the electric field gradient. And the electric field gradient is the second derivative of the electric potential with respect to the electron coordinates. So you have a rank 2 tensor again here. And the electronic contribution is calculated with the electron density as shown here. And so this naturally lends itself to analysis. I'm writing here the two expressions for the electronic, and there's also a nuclear charge contribution to the field gradient. And so in the implementation in ADF, they're both analyzed together. So what I do here is I'll write the nuclear contribution basically as an electronic operator and absorb this. So the nuclear contribution gets weighted as well with the electron density, just like the electronic contribution. And then you can straightforwardly partition the electron density, in my case here, in terms of NBOs or NLMOs again. But any other set of localized orbitals will do just fine as well. Qualitatively, and this will be interesting for the example. So for instance, here's the electronic field gradient that you, rather the operator. And so if you apply this to a set of p orbitals, and you look at the z component, the z component of the electric field gradient, a 2pz orbital, if occupied, would contribute -2 times a constant, and perpendicular px, py orbitals would contribute +1 times the same constant each. And so if you add them together, you get the contribution from a filled shell, which is 0. Right? A spherical atomic p shell will not generate a field gradient. So the analysis will then focus basically, and we've done this numerous times in subsequent publications, the analysis can then focus on basically the slight imbalances in the occupations of these orbitals here to explain how a certain field gradient arises and how you can explain its magnitude. maybe I will skip this because I want to have time to perform the demo. So here are some calculations. In this case, we looked at aluminum field gradient tensors. Here an aluminum Cl3, methyl 3 compound, and here's a related compound with a larger ligand. Calculated VZZ, which is the electric field gradient at the aluminum, and the Z coordinate is bottom to top. So small here in AlCl3, much larger in the methyl compound, and comparable here in the actually experimentally synthesized mesothyl compound. And this is the converted to the nuclear quadrupole coupling constant. So here the calculation agrees very well with the experiment. And so you may ask the question, why is the field gradient in this chloride complex so much smaller? So we can do the analysis now with NBOs and NLMOs. And so there are bond contributions, there are lone pair contributions. Let me see if I have this here on the next slide. So in each sigma bond, we have a contribution here to the field gradient. And if we analyze this in terms of NBOs instead, so here we have sort of the delocalization needs to be considered through the occupation of the NBOs. We'll find that there is a negative contribution from the 3pZ orbital, which is this number 33. I'll show this to you in a couple of minutes. That makes the field gradient in the chloride complex much smaller than it is in the compounds with the organic ligands here. And so that means effectively that the chlorine can donate. So here's the chlorine, here's the chlorine and the bond to the aluminum. And here's the 3pZ orbital of the aluminum. So the chlorine has p orbitals that are occupied. So it can donate electron density to that 3pZ orbital of aluminum. And in the methyl and the mesothyl compound, that orbital has no occupation. And so you get a very strong field gradient, basically because the aluminum has electron density around it only in the plane of the coordinating groups, but not perpendicular to it. Now you get this pi donation from the chlorine, and in the analysis, this shows up as basically the difference between these compounds. Okay. So here are some other bonding environments that we studied as part of this little tutorial review here, if you're interested in electric field gradients and their analysis with the help of localized orbitals. This is where this is all discussed together with my experimental collaborator, Rob Schurker. And before I get to the demo, just wanted to mention briefly that these analysis methods for shielding and J-coupling, we just recently wrote a small piece for ChemPhysChem, again, sort of explaining this in a little less detail and more application-oriented than the original publications. And that work is also now funded by a grant from the Department of Energy, asking us to look at what is special about platinum and why is platinum so useful in catalysis. And so we're using these analysis techniques now in conjunction with solid-state NMR to figure out what makes platinum so special. So it turns out almost 20 years after these developments, this is still useful. And so that's what I wanted to share with you. Okay, now let me stop sharing this. And I want to now try and share part of my desktop. Let me see if I can do that. So here, there's an advanced setting. And you should be seeing now a portion of my screen. Maria, if this doesn't work, please tell me. So I'm going to move the presentation down here. and go back to this platinum analysis right here. Last week I set up a calculation here for this PTCl4 2- complex that we discussed. So here it is, and to reproduce the previous calculation, I used the QZ4P basis set on the platinum and the TZP ZOR basis set on the chlorine atoms. Therefore, the graphical interface shows these two different regions here in which the basis sets are defined. This is a FPBE calculation, spin orbit, and there's a solvation model applied because the measurements are in solution. And then what's important here is that you perform NBO analysis for the NMR that will trigger the sequence of calculations. So what will be done is a scalar relativistic calculation followed by NBO to calculate NBOs, so occupied and unoccupied NBOs and NLMOs. So we need the full flexibility of the AO basis at that point. And then the script will repeat the calculation and then run the spin orbit part of it. And when you visualize the output and go to, I think NMR is in other properties right here. So this is the total calculated shielding here, which is very similar but not identical to what's in the old publication. I believe this has mainly to do with the fact that the ADF code now uses much better fitting procedure for the density than it used to. And then I will scroll up a little bit. And let me see. Okay, and then so somewhere in the output of this, you can find a section NLMO contributions to the isotropic shielding tensor. There is by default a print threshold so that small contributions will not be printed. So you don't get these endless listings in the output. But if you don't want that, you can set the print threshold to 0. And then paramagnetic and spin orbit, diamagnetic, and then here's the total calculated shielding contributions. And so, for example, we see here an NLMO with a contribution of about 44.99. Here in the old publication, it was minus 44.73. So there are small differences that have to do with technical improvements, mostly in the ADF code. And if you want to see what this orbital 58 looks like, you head over to the ADF view program. So in the menu here, you would pick view, and then there is a file that's generated that includes the NLMOs. And so we're gonna visualize those, except I need to move this out of the way for a second. Oops. Yeah, see, that's the demo effect. Mainly it doesn't work. Okay, so I think 58 was the one. So NLMO 58 was the one that produces most of the deshielding around platinum, and that's exactly the one that we identified here as the XY. That's this 44.73, and it was very similar in the modern calculation. So you can pretty much reproduce this table straightforwardly from the calculation just by copy pasting what you can find in the output file. Do I have a couple more minutes to show the EFG analysis? Okay, I will do that then. So let me open the other calculation that I prepared, which is the AlCl3. Okay, here it is. Also a simple molecule. And let me just look at one detail. Yeah. Oh, here it is. There's an option to view the input that will actually be ran. So in this case, field gradient tensors only have scalar relativistic analysis, where in the process of implementing this for spin orbit calculations. So there's the single point calculation, and then it goes into the, there's the interface for ADF and NBO. What happened there? And then it will run this here. And what's important is that after the NBO step, there's a file 1adf.rkf that contains the list of NBOs and NLMOs for visualization. So let's see if we can run this. So hopefully this will work. It shouldn't take long, right? This is a small molecule. So let's see, it looks like we're done. And let's see the output. Okay, let's bring this over here. And then I have to scroll for a little bit to see the NBO analysis. At the end here. Okay, right here. So this is the beginning. That's the AO response functionality in ADF that we developed some time ago. There's a request here for a field gradient analysis. There's contributions from the canonical MOs, and in this case, we're interested in the NBO analysis of the field gradient component number 3. Here are the NBO contributions. And in the modern NBO versions, this PZ orbital on the aluminum is written as a low valent orbital. You can see that it has an occupation of about 0.25 that comes from this pi donation from the chlorine ligand. And it has this comparatively large negative contribution then to the field gradient, so making its magnitude much smaller. So let's see if we can visualize this. Let's see, view. Here we go. And then I need to open this file generated in the run script. I talked with one of the developers last week. They're going to rename this to NBO-NLMO-ADF.RKF, so it's perfectly clear which of the files we should be visualizing. And then let's look at an isosurface, and let's look at the NBO. And here I'm interested in the NBO number 33, which is right here, this low valent NBO. That's the PZ orbital that receives the donation from the chlorine ligands. And here is one of the chlorine NBOs. You can see here in the list here also there's the occupation listed. It's only 1.91. It's not 2, and that indicates that you have donation. So if I visualize this same NBO as an NLMO, number 29, you will be able to see the donation right away, and there it is. So now you can see how it directly donates into that PZ orbital on the aluminum, and thereby reducing the field gradient. All right, that's all I wanted to say today, and I'm very happy that demo didn't totally crash on me. I hope you could see my screen, and I'd be happy to answer any questions.
Thank you. very much, Jochen, for the presentation. Now we have time for some questions. While people are thinking about their questions, please let me remind everyone that next week will be the last webinar of this spring webinar sessions. It will be on Wednesday, 3 p.m. And we will have Robert Ruger from SCM, our architect, and Egin Torum from Symbeyond. And they will talk about the project. We are collaborating, both SCM and Symbeyond, about multi-scale modeling of OLEDs. And this was the development of the multi-scale approach was a previous project, and now we are developing the mechanisms of the excitations that are taking place in the devices. So please join us. You will receive an invitation after this webinar. And yeah, let's see if we have questions. Okay, not yet. Let me ask you a question. Well, it can be very silly, but I was just curious, this platinum-titanium complex, why, do you know an intuition, or have you studied why the J coupling is so strong in this complex?
Yeah, I can say a little bit about that. So it's platinum and thallium, and in these heavy elements, the 6s orbital has a very strong relativistic contraction and stabilization, and the electron density of these orbitals at the nucleus increases dramatically when you turn on relativity. And so the coupling constant is mainly driven by what's called the Fermi contact mechanism. So that's spin density induced right at the nucleus and transmitted through the electronic system, detected, so to speak, by the other nucleus. And the more S electron density there is at the nuclei, typically the larger the coupling constant is. Although one needs to be a little bit careful that not to interpret these properties purely as a ground state property. They also are sensitive, of course, to how the system responds to the perturbation. But when you have 6s contributions, and both of these metals do, you can get extremely large relativistic effects. And that is one of the main driver that makes the coupling constant so large. Okay, I'm happy to see some questions in the chat here. So let me, David asks, is it possible to do the NBO NMR analysis for paramagnetic NMR? So I suppose you have in mind the effects, the paramagnetic effects when you're dealing with open shell complexes. The answer is yes. In a sense, you can do that by analyzing the hyperfine coupling constant accordingly. And that's an analysis that follows very similar steps to what we do for the electric field gradient. And we did publish a little bit on this topic in the past, but I don't know the citations off the top of my head, but if you send me an email, I will direct you to the relevant publications. We have done this before. So the paramagnetic contribution gets split up into a product of a hyperfine tensor times G tensor, and the hyperfine tensor can be analyzed along the same lines as the field gradient. Okay, next question, a little irrelevant to current topic, want to know I'm not sure if I understand this other question here. It comes also through a direct message, so the rest of the audience can't see it. This is a question, I believe, meaning whether, which elements can be used to study these effects. So basically, you can do the calculation for any type of nucleus that you like. The experimentalists need a nuclear magnetic moment to observe nuclear magnetic transitions. So the nuclei have to have a spin, and to observe the field gradient, the nucleus must have a quadrupole moment and therefore has to have a spin greater or equal to 1. Lucas asks for the field gradient analysis between AlCl3 and AlMe3. Could the back donation in principle also come from the CH sigma bond? I believe there may be a little bit of an effect like that, and if it's there, you should see it in the analysis. So I guess what you have in mind here is a type of hyperconjugation, which is also a delocalization effect. In fact, we've analyzed that for paramagnetic NMR. We've analyzed hyperconjugation pathways that transmit the hyperfine coupling constant from the open shell metal center to a faraway ligand nucleus. So the answer is yes, in principle, but the effect is not as strong as the effect from the chlorine donation. The next question here by Yuya is it possible to completely ignore spin-orbit effect, only concentrate on the paramagnetic term? The answer to that is yes, you can. If the spin-orbit effect is important, then of course ignoring that means you will not get a good comparison with experimental data. But people have for example, proposed that the paramagnetic component of the shielding tensor could be very useful for analyzing chemical bonding in a system. Steve Little, for example, has published some really nice work on this in recent years in the context of actinide chemistry. But the paramagnetic component of that shielding tensor is not in itself an observable. So you would have to have some a priori knowledge about whether that is the only important contribution to the shielding or not. But that, I would say, you can figure out by calculations. So the answer to that question is a qualified yes. All right. Please write again in the chat if I did not properly answer your question, or if somebody else has a question, I'd be happy to address that. Thank you.
Yeah, we have still, people are thanking you. Yeah, we have still.
It's time now.
Yeah, it's almost 1 hour. So yeah, thank you very much, Jochen, for the great presentation and demo, and for your time, for accepting the invitation to participate in this webinar.
Thanks for hosting, and thank you all for listening.
Thank you very much.